So in the previous topic, we came up with a series of really useful relationships for accelerations and velocities and positions, but we're still left with the question, why do things move the way they move? And this is a question that's pondered by scientists throughout history. In fact, for a very long time, the question was thought, why do things move at all? And people tried to come up with ideas of what causes motion. And starting with Galileo and being furthered by the work of Isaac Newton, it became apparent that if you looked at the universe really clearly, it wasn't things moving that required explanation, it was things changing the way they move. And again, in language that you now understand, what that really means is that you don't need to explain the velocity, you need to explain the change in velocity, the acceleration. And that's wrapped up in a statement that constant velocity motion is the natural state of objects in our universe. It just turns out that's the way it is. You don't need to explain why something's moving past you. If as it moves past you, it accelerates, that's when you need an explanation. And that's wrapped up quite tidily in a statement of what we call Newton's first law of motion, that constant velocity motion is the natural state of being. A body in the absence of any forces will move with constant velocity. Of course, that just raises the question, well, what do forces do then? What forces do are change the velocity. They cause an acceleration. And again, Isaac Newton and many other people along the way have looked very closely at what happens when you apply a force to an object. And it turns out that if you apply a force to an object, you cause an acceleration, and the acceleration points in the same direction as the force. Just as importantly, if you double the size of the force, you get twice the acceleration. And that leads us to a nice description where acceleration and force are closely linked. But something else is important as well, and that's the idea of mass. If you apply the same force to two objects, you don't always get the same acceleration. If one of the objects has a large mass, it ends up having a much smaller acceleration, and the small mass object gets a larger acceleration. Now, Newton wrote that down very, very nicely in what we now call Newton's second law of motion, where the acceleration equals the force divided by the mass. And you can see in this equation that force is a vector and acceleration is a vector, and they point in the same direction. Now, of course, you might have more than one force acting on an object. If that's the case, then what you need to consider is what we call the net force. The net force is what you get when you add up all of the forces that you have acting on your object. So you might have one force, and then you have to add, say, another force, and then you might have to add a third force, etc., etc. Importantly, as I've indicated, this is a vector sum. So you've got to take into account the direction and the magnitude of these forces. Some of you might already know Newton's second law, and you might have seen it written slightly differently. It might be written in your version as the force, in particular the net force, equals mass times acceleration. And probably only slightly less popular than E equals mc squared is F equals ma. I like to write it as A equals F over m because it reminds me that the acceleration is due to the force, not the force being due to the acceleration. And as we'll see later, that's a very important distinction to make to get it just right. Now, the other thing about forces, as well as causing accelerations, is that forces come along in pairs. Again, if you look around in the universe, this is something that seems to happen everywhere. So it goes by the title of Newton's third law of motion, that if one object pushes on another, that second object pushes back on the first. Or if you like, when your foot kicks a football, it exerts a force on the football which makes it accelerate. What you can't avoid is that the football exerts a force back on your foot. Interestingly, those two forces are exactly the same size and point in exactly opposite directions. And this is what we call an action-reaction pair. In fact, some people know Newton's third law by a fairly standard phrase: for every action, there is an equal and opposite reaction. So a strange example to consider, but one that's quite helpful, is the Earth pulls on me with a gravitational force. By Newton's third law, I pull on the Earth with a gravitational force of exactly the same size, but in the opposite direction. Now, if I fall off a cliff, the Earth pulls me down quite rapidly, a large acceleration. I'm also pulling on the Earth. The Earth doesn't move very much because it still obeys Newton's second law, where you've got a force pulling on it, but its mass is so enormous, its acceleration is essentially negligible. What we're going to do now with these three laws of motion is look at a few examples such as gravity and friction and see how we can apply Newton's laws to really calculate the motion of objects.